Now, how do you work out the magnetic field in some region of space? So let's say there's a magnetic field here. How do I work it out? Well, once again, I need some charge. So let's say I put some charge on this ball. If the ball is stationary, the magnetic field has no effect on it. But if the ball moves, then there's a magnetic force. The magnetic force is rather strange, so it's not in the same direction as the magnetic field. So let's say we have a magnetic field pointing that way. If the ball moves in the same direction as the magnetic field, there's no force on it. The ball has to move in some other direction. So let's say the magnetic field goes that way, and the ball is now going up. So the velocity of the ball is in this direction, and the magnetic field is in that direction. In that case, the force is actually going to point towards me. So it's at right angles, both to the motion of the ball upwards and to the magnetic field, which is that direction. So they're all three things at right angles. The way you work out which direction it works is the right hand rule. So here's my right hand. What you do is you look at the velocity, which is this direction, and the magnetic field, which is this direction, and you work out what you need to do to turn the velocity till it points in the direction of the magnetic field. And you curl your fingers so they go from the direction of the velocity to the magnetic field direction. So it's curling like that, from velocity to magnetic field. And then the direction your thumb's pointing, which is towards me, is the direction of the force. Let's do another example. Now let's say I drop the ball and the magnetic field is pointing towards you. So the magnetic field's in this direction and the ball's going downwards. So the velocity is downwards, magnetic field is this way, so we need to go from the velocity to the magnetic field, which tells us the force is going to be this direction. And once again, it's at right angles, both to the motion and to the magnetic field. Now this is what happens if you just got a charge flying around. A much more common situation in most practical applications is to have charge going down a wire, called an electric current. So here we've got a wire, and so let's say we have some charge going down the wire in this direction, and there's a magnetic field pointing upwards. So again, the same right-hand rule applies. The wire, if the wire's in the same direction as the magnetic field, there's no force. It has to be at some angle to it, preferably a right angle to make the force as big as possible. So magnetic field upward. Here, that means the charge is moving that direction. It's actually negative charges going the other way, but just pretend it's positive charges. So we have to go from the velocity, the current, to the magnetic field. So we're curling our fingers like that. So that means the force is going to be in this direction. It's going to push the wire towards you. Now let's look at the equations we need to work out the force due to a magnetic field. Now these are vector equations. The force is a direction. So for a moving charge, the equation is the force vector is equal to the charge times the velocity vector of that charged object times the magnetic field. If you're talking about a whole wire, it's basically the same thing. For a wire, the force is equal to the length of the wire times the current, which is a vector pointing along the wire in the direction the current is going, times the magnetic field. How about the direction? Well, the direction, as we just saw, comes from the right-hand rule. So it's going to be, if you have a magnetic field in this direction and velocity in that direction, you curl your fingers from the velocity to the magnetic field, and it goes off in that direction. What if the velocity and magnetic field, or the current and magnetic field, are not at right angles? Well, it turns out that the strength of the force, so that's the amplitude, the modulus, so the vertical lines meaning just how long the vector is ignoring the direction, is equal to L, the modulus of the current, the modulus of the magnetic field, times the sine of the angle between them. So if you've got a magnetic field like this and a current like that, this angle here is theta. So you can see that when they're at right angles, you get full strength, as you've seen before. As the angle between them gets smaller and smaller, sine theta gets smaller and smaller, and then they're pointing in the same direction, that goes to 0. Now there is a neat mathematical way to do all of this, and for that we have to factor in what we actually mean by multiplication between two vectors. Now it turns out that multiplication between two vectors is something you'll do in maths. There are two types. There's what's called the dot product, written as a dot, which we'll see later in the course, and this is the cross product. And it works like this. If we have two vectors, A cross B, what you do is rather complicated, but has a pattern to it. This is the vector, so the cross of two vectors is a third vector. What you do for the x component of your answer, of the multiplication, you take AYBZ minus AZBY. So what you're doing is the x component of A cross B actually doesn't involve x, it just involves the y and the z. Likewise, the y component is AZBX minus AXBZ, so it just involves the things not in that particular term, and similarly over here. So hopefully you can see the pattern. Now a slight caveat, this works for what are called right-handed coordinate systems. That's something like this, x off this direction, y up here, and z in that direction. If you had z going the opposite direction like that, that's a left-handed coordinate system, and there'd be a minus sign in front of all this. But in this course we'll just stick to right-handed coordinate systems, and so this is how you work out the cross product. So what you can do is, if you know the vector form of the current and the magnetic field, you just go and do that cross product, and that will tell you the vector form of the force. And that automatically factors in the right-hand rule for which way it points and the sine theta. So you don't need to put the sine theta as well if you're doing it this way.